Okay, so when we were doing the examples so far in section 6.1, one thing that you may have noticed is that in each case, the bounded region was perfectly adjacent, entirely adjacent to the axis of rotation. Just really quickly, if we were to kind of look at the sketches of all the ones we've done before. So here, that region was adjacent to the axis of rotation, x, no gaps. In the second one, the region we were rotating was entirely adjacent to the line y equals 4, no gaps. There's a gap between the x-axis and it, but that's not what we were rotating it around. Even when we did vertical axes, perfectly adjacent to the axis of rotation, no gaps. Perfectly adjacent to the axis of rotation, x equals 4, no gaps. The result in this case is that each one of those solids of the cross sections were perfect discs. They were solid, there were no holes or anything like that, perfect circular discs. We're going to consider a situation now is, well, what if it's not all perfectly adjacent? What are the shapes that we then generate, and how do we go about finding and generalizing volume? Well, let's start with an example that I've got drawn here. We've got two functions, f of x and g of x. And we want to consider the region bound in between them over the interval from a to b, and we're going to then rotate that about the x-axis. So let's kind of zoom in here. So here's our region between a and b. So this is the area that we have trapped in between these two curves over that region from A to B. Now what we're going to do is we're going to take this region and we're going to rotate it around the x-axis. So notice, all of a sudden we can see that there's difference because there's this gap in between that area and the axis of rotation that's going to result in a gap in our solid. So let's kind of see if we could think about what this looks like. So we've got our top curve f of x, which, as we try to three-dimensionalize it, is going to come up and down like that. And if we were to rotate that around, we would have a circle, and then this also gets rotated around, and we'd get a curve that would kind of look something like that. So that's just the outer curve f of x that's been rotated around. But if we consider that we've also got this inner curve right here, f of x, that is, maybe it's starting way down here, and it's rotating around, and then it sort of within, you kind of think about within it, it's coming up here, it hits, and it leaves sort of a gaping hole in there. So it's almost like a deformed roll of toilet paper, or if you guys ever ate the snacks combos where there's the pretzel on the outside and the cheese shoved to the inside, this is kind of like a hollowed out version of one of those. So we've got a solid where there's a hole in the middle because of this gap right here in our area in the axis of rotation. So how do we go about finding this? Because if we look at the cross, or the volume of this, if we looked at the cross sections, so let's say we went back up here and we had drawn a cross section of our area. If we were then to take that cross section and rotate it around, so maybe that existed here at x, and we'll put that along the x-axis. So we've definitely got the outer part that gets rotated. And then here on the inside, this also gets rotated around. So essentially what we've got here is we've got a disk with a hole in the middle. And we often refer to this as a washer, and that's why we we tend to call this the washer method. So if we think about it, this solid could be sliced up into a series of little washers or discs with holes in the center. So much like where we, in the disc method, we added up all the discs, now what we're going to do is we're going to add up all of these washers to get a better idea. Now, my drawings may be kind of a poor representation of what's going on, so don't hesitate to go into the textbook. They've got some nice computer-generated graphics that might be more helpful than what I was able to draw here. Regardless, what we want to do is, now that we know that these are washers, we need a formula to calculate the area of each of these washers. With the disk, it was as simple as just pi r squared, but the area for this is going to be a little bit different. So if we take one of these washers, and I'm going to kind of tip it on its side so we can look directly at it. So it starts with a circular outer radius, which again is a perfect circle. So we'll refer to this as our outer radius. And we'll call this big R of x. And then there's our inner radius that was created by that other boundary function. And we'll refer to this appropriately as the inner radius. And we distinguish this by calling it little r of x. And then, of course, right in the middle is our axis of rotation right there. So again, what we're interested in calculating is what is this area, the area of the actual surface of the washer, because if we can generalize that, then that will give us, a means using the definite integral to find the volume there. So with this in mind, essentially what we've done is we've taken to find this area of a washer, it's going to be the area with the outer radius and then we subtract the area that would have been generated from the inner radius. And that gives us the full area of the washer. So it's just a matter of subtracting. So if we kind of took this a little further and then considered A as a surface area as a function of x, it's going to be pi times the outer radius squared, just like the disk method, except we subtract the area of that inner disk, pi times little r of x squared. And to make things a little bit easier on us, what we tend to do is factor that pi out, and then we've just got outer radius squared minus inner radius squared. Notice we are squaring them individually, not the difference being squared in this case. All right, and just to be consistent with the notation here, I guess we do that. Okay. So that's how we would calculate the area of the washer. And then it's a simple kind of reintroduction of the integral, in that the washer method will be used if there is a gap in between the axis of rotation and the area, as we saw here. This is the way that we're going to want to set this up using the washer method.